So now let's look at how we can measure enthalpy change of combustion reactions in the lab. Now, combustion occurs all around us. We do it, we burn fuels, we burn methane gas, we can burn alcohols, and you can even burn metals with oxides. Because what is combustion? It's basically when you burn 1 mole of something in excess oxygen. That's combustion. You've seen that in alkanes in organic chemistry, and alkenes also. Alcohols combust. All organic compounds undergo combustion. And how are we supposed to find the enthalpy change of such reactions? Now remember, you will not be asked to find the enthalpy change of combustion reactions of gases, because you can't do that in the lab. But you can do is that find the enthalpy change of liquid fuels like alcohols. And very simply speaking, you burn alcohol, it produces heat. You burn ethanol, it produces heat. So like, for example, any alcohol or fuel reacts with oxygen. This is the word equation to make carbon dioxide and water. I'm not balancing this, just saying what happens. And the reactions are highly exothermic. They produce heat. But I cannot put a thermometer inside an alcohol and burn it. It'll just burst the thermometer. So what we do is this. What we say is that, okay, we can have a reaction that produces heat, but how do I find that the heat evolved during that reaction? By not measuring the temperature of the actual reactant, but by measuring the heat gained by water. Now the problem is, the previous cases one of the reactants was water, either as a solvent for acids or alkalis, or even water to which you're going to add a solid. Here there is no water in the reactants, and this is not the water I'm talking about, this is just steam. So what we do is we react the alcohol and oxygen, and then the heat they produce, the flame they produce, is used to heat water in a setup that looks like this. This is the setup we use. We have something called a spirit burner, which literally has the alcohol in it. This has the alcohol. Now this is an inverted diagram taken because of black, so this flame looks blue, but it's supposed to be a reddish flame. So you put the alcohol here, and then you light fire to it. And the heat it produces via conduction will heat a known mass of water. And the beaker is generally a good conductor of heat, so we take copper, because you want the heat transferring here. Unlike the previous cases, you want the heat transferring from the base, but you might not want the heat escaping from the side. So generally, a perfect or a better version of this setup, let me show that to you, includes things like lagging and even a draft shield, which helps prevent heat loss, because the flame has the ability to lose out heat according here and here. You see, they can lose heat here and here. So what we do is, so the idea of, before I give you the perfect setup or the better setup, the idea is you take alcohol in here, let's say the alcohol whose combustion value I want to find, because I want to find how much any combustion reaction takes. So you burn some of the alcohol, some, not all of it, and whatever you burn, you can find the difference in mass. And the alcohol that you burn is going to raise the temperature of water. And knowing the initial temperature of water and the highest temperature of water, you can find the heat gained by water. And that you will assume is the heat lost by this reaction, assuming there's no heat loss to surroundings. And that's the method we use. So we have a separate, we're not mixing my reactant with the water. They're independent here. This is called a calorimeter, where you are finding the calories of combustion. This setup that I'm just showing you on the right is a better version of the setup. When you're going to be doing second year labs in theory, paper 5, planning of labs, this stuff will be important to draw. That if you want to burn any fuel, liquid fuel, and finding its combustion enthalpy, you will place the beaker as close to it as possible. Have the beaker be of a metal container, not a glass beaker. And you will lag the sides by either mineral wool or some other foam, but not normal foam, because it might catch fire. And you'll also want to lid it, because you don't want evaporation taking place. And the thermometer inside measures the heat gained by the water. So that's the setup that you should keep in mind. They will not ask you to draw the setup in AS. You will not even carry out this reaction in the lab. But in second year planning, this will be very popular in some of the lab exams that have come up. So you'll have to draw this out and all that. But right now, forgetting this, right now what is important is being able to use the math for this to find the enthalpy change of a reaction. They tend to, for example, if I take methanol, they'll give you the, let's say I give you that I'm burning methanol. So just let's use this example first. So they'll give you a certain amount of methanol initial and a certain amount after burning. So the difference in the mass is how much methanol, for example, burned. You'll give you the initial temperature and the final temperature. So you'll have the temperature rise. And using those two things, you'll find the enthalpy change of combustion. And let me now do that math for you. So let's say I have the same setup, and I'm telling you that methanol, there were mass in it. So in fact, I have the table with me. So let me actually draw that table and give it to you. So the table has the data of the initial mass and final mass and the volume of water taken. Now, if the volume of water is given in cm cube, remember water, pure water is, it's 1 gram per cm cube. So let me just paste that table first and then, yeah, let me do that for you. So the table data is, one second, right there. Yeah. So this is the table. The mass of the burner plus methanol initially, mass, final mass. The difference is the mass of methanol burnt. The temperature of water before the experiment was 23, and the final, when the reaction was stopped, was all the way up to 47. And the volume of water used, or the mass of water used, was 200 grams. And so how do I use this information? Well, first, the method is kind of the same. You still have to have a Q. In this case, you will not talk about the methanol burning. You will talk about the water gaining heat. So there was 200 grams of water. Let's say the C is 4.2 or let's say 4.18 now. And the temperature rise. Well, it was 47 minus 23. And using this, you will find the enthalpy change or the heat gained by water. So 47 minus 23 is 24 into 4.18 into 200. This gives you 20,064 joules or 20.064 kilojoules. Now, that's just the heat gained by water. But you might wonder, well, I don't have anything else. Well, I have the mass of methanol burnt. Now, the equation might not be handy, but I'm still going to give it to you. Methanol's burning is this. CH3OH is methanol, forms carbon dioxide and 2 moles of water. That's 2 into 4, so I need 2 O2s, right? No, I need 1.5 O2s, not 2. Or 3 over 2 is better. Now I'm writing 1.5. Yeah, it's better either way because it's space. So that's the equation. But I don't care because I just need it for, because the delta H for this reaction is the combustion, and I need it for per mole of, so it's really per mole of methanol. Per mole of methanol is what I want to find out. So this is the enthalpy change or the heat change for a certain mass of methanol burning. For that, I want the formula mass of methanol. So the formula mass, or in this case, it's a organic compound, so I can say MR. So the MR of this fellow is 12 plus 4 oxygens plus 16. That's 20, 32. So now, what I want to know is the moles of methanol burning. So it'll be mass over molar mass. What's the mass burnt? It's the difference in mass only. So it'll be this minus this. So that's 2.38 or 238 minus 86. So let's do it for 238.86 minus 236.61. So the mass burnt was 2.25 only over 32 will give you the moles. And this comes out to approximately 0.07031. That's the moles. So I've got the moles and I've got the heat. So what I need now is delta H. Again, the formula is heat over number of moles. And since the temperature rose and all combustion is exo, this is minus. And so minus of 20.064 over 0.07031. So literally that's what you do. 20.064 divided by 0.07031. You get, I need some space here. This comes out to 285. So minus 285.4 if you want one decimal place. But minus 285 is perfectly fine. And that's the delta H of this reaction, which is methanol burning using the data they've given you. All right.